Today I'm looking at the reactions of alkanes, and the reaction in particular is halogenation. This is introducing a halogen, something like chlorine or bromine, into an alkane. So for example, if we were to take methane, we could react it with chlorine to make chloromethane and hydrogen chloride. HCl here could be considered a byproduct of the reaction. And this little person here, chloroalkane, is an example of a haloalkane, or sometimes they're known as halogenoalkanes. Now, in order to make this reaction happen, let's have a look at methane. I'm not sure why my hydrogen's got a little hat there, let's get rid of him. The bonds in alkanes, whether they're carbon-carbon or carbon-hydrogen, are very strong. So we need some pretty extreme conditions to persuade our alkanes to react. And those conditions are high energy UV radiation. So the type of reaction we've got here is halogenation. The mechanism by which this reaction happens is known as radical substitution. And radical substitution, so that's my mechanism explaining how the reaction actually happens, occurs in three distinct phases. So let's have a look at the first one. During the first one, and this is known as initiation, we use UV light to break the bond in the chlorine molecule. So let's have a look at this. There's my pair of electrons in the covalent bond. The action of UV light causes homolytic fission. And what that means is that the bond breaks evenly. So one electron ends up on one chlorine atom and the other electron on the other chlorine atom. Note that I am using half-headed arrows, and that is indicating that I am moving a single electron. If we're not using homolytic fission, the more usual way for a bond to break, in contrast, is heterolytic fission. So for example, if I were to take an HCl bond with its pair of electrons, then during most chemical reactions this bond would break and both the electrons would move to the chlorine atom, and I'd end up with ions, positively charged hydrogen cation and a negatively charged chloride anion. So in heterolytic fission we have got a double-headed arrow to show the movement of a pair of electrons, and both electrons are moving to one of the atoms. However, that's not what's happening here. So writing this as an equation, we would write Cl2, high energy UV radiation, forms two chlorine radicals, and this dot here indicates that we've got an unpaired electron, which is the trademark of a radical, and radicals are very, very reactive, which is what we need to persuade our alkane to react. In the second stage of our radical substitution mechanism, we have propagation, and propagation takes place via two steps. In the first step, we are producing the byproduct, and I'm emphasizing that because it really helps to understand the mechanism if we're clear. So here's my methane molecule. I've got a carbon-hydrogen bond and I've got a chlorine radical. This bond breaks again by homolytic fission. One electron goes back to the carbon and the other electron is used to make a bond with the chlorine. Now this is a very slightly exothermic reaction because I'm going to make a hydrogen-chlorine bond, and that is slightly stronger than the carbon-hydrogen bond we broke, and I've got a new radical. This radical here is a methyl radical. So we can see in propagation reactions we start off with a radical and we end up with a radical. Essentially, this is a chain reaction. So as I said to begin with, step 1 produces the byproduct in this reaction. Step 2 produces the organic molecule product that we're after. So step 2, we have our methyl radical colliding with a chlorine molecule, and again we're going to form a bond using one electron from the methyl radical, the unpaired electron, and one from the chlorine-chlorine bond, and we're going to produce another chlorine radical. The chain reaction continues. So we have here our chloromethane and the chlorine radical, and around we go. So again, this is an exothermic reaction because this carbon-chlorine bond is considerably stronger than the chlorine-chlorine bond we've just broken. And the third and final stage of our radical substitution mechanism is termination. And in a termination step, we have two radicals meeting and forming a non-radical, so the chain reaction is ended. And there's various possibilities. We could have a methyl radical forming a bond with a chlorine radical to form more chloromethane. We could have two methyl radicals bumping into each other and forming ethane. So in terms of drawing that one out with curly arrows, for example, we would be looking at something like so. So one radical, two radicals, and they're both putting in their unpaired electron to make that new carbon-carbon bond that we would see in ethane. So that would be the product. I hope you can see that in radical substitution reactions we end up with a whole variety of products. Firstly, because we've got different types of termination reactions, but also because our propagation product, by chloromethane, can undergo further substitution. So another chlorine radical could abstract a hydrogen to form CH2Cl plus HCl. And then that could go on to further react to form CH2Cl2, and on we would go. However, if you do this with the alkane in excess, then we're far less likely to have multi-substitution going on. I want to finish by having a think about radical substitution of propane. So propane, we've got 3 carbons, each bonded to hydrogen. Now when you look up the bond strength, the bond enthalpy of a carbon-hydrogen bond, we're talking about an average bond enthalpy. And what we find is that the carbon-hydrogen bonds for the terminal carbons are stronger than the carbon-hydrogen bonds for the middle carbon. So that is slightly weaker. We also know that if we were to abstract a hydrogen, so let's say, let me change my colour here, I have too many arrows. So let me say I've got a chlorine radical and it abstracts that particular hydrogen and the other electron ends back up on that carbon atom. So my product would be this carbon radical. It's got a hydrogen and an unpaired electron. We find that this intermediate, lots of new words today, this intermediate carbon radical is actually more stable than if the, let me just take that away, is more stable than if, say, the chlorine had taken a hydrogen off the end. So producing this radical intermediate here. Put my hydrogens on. So that is a more stable intermediate than if I've got my radical on the end carbon. The result of both of those points is that when we are looking at the reaction between propane, so CH3, CH2, CH3, and a halogen, could be chlorine, it could be bromine, then we find that we are far more likely to have this as a product than a chlorine at the end, CH2, CH2, Cl. Far more likely than would be expected simply by chance. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.